7, and what we are doing is we are studying something called linear momentum. So what is momentum? Well, if we have mass if we have mass that's moving, the product of the mass and the velocity is the momentum. So momentum is basically mass that's moving. It is a vector, so the direction is going to be very important to us. The symbol is small letter p. As I said, it's a vector, so that's what that arrowhead means. And the units would be kilograms meters over a second. So they're not the nicest units, but a lot of the things we've been using lately are units that were named after people. So you see newtons, it's a derived unit, and it's named after people. And joules is a derived unit named after James Joule, and watts is a derived unit named after James Watt, I think. Okay, so the formula for momentum, and I'm going to draw a line again, it's basically this. Small letter p for momentum, it equals the mass of the object times the velocity object. And that's our formula right there. So when we talk about momentum, the mass times velocity will give us the amount of momentum. And I like to think about momentum in terms of inertia. I would think that if there's something that's very, very big and has an awful lot of velocity to it, then it can't change what it's doing easily. And inertia is basically the tendency of an object to maintain whatever state of motion it's in. So when we're talking about momentum, if we had a very, very small mass, like the mass of a toy car, and it was moving at a very, very small speed, like 1 meter per second or so, well, it doesn't have much momentum, and that means you can change the direction of the toy car pretty easily without much effort. On the other hand, if you had something very, very massive, something like a tractor-trailer, and it was driving down the highway at a very big speed, well, the product of these two big numbers would come out to be a pretty big momentum. And something with a big momentum, it's a vector and it can't change easily. So a big tractor-trailer driving down the highway, it can't change its directions suddenly, quickly. A small mass of, say, a bullet moving at an incredible speed would also have a big momentum, a huge momentum. So if the bigger the momentum, the harder it is to change what it's doing. Bullets are not easily deflected from their path. If you had something huge, maybe like an elephant, and it's just walking at an incredibly slow pace, well, then it is very easy to change its direction. So the more product of mass and velocity, the more momentum, and the harder it is to change things. Typically, we don't want to know what is the momentum of one individual piece. Typically, we are trying to figure out what is the momentum of all of the pieces combined that are moving simultaneously. So we look for the momentum of the system. So the momentum of the system would basically be written this way, if I were to draw a line. So we would talk about P, the total momentum, which would be the momentum of the first piece, plus the momentum of the second piece, plus however many pieces we would have. So we could say the momentum of the total system equals m1 v1 plus m2 v2 plus however many more we have. Okay, and that would be talking about the total momentum of the system. Okay, as an example, I could have some toy carts. So let me have this toy cart as 1 kilogram moving to the right at a speed of 2.5 meters per second. And I can have in a second toy cart, which could be it could be a little bit bigger. I could call this over here 1.5 kilograms. How about if it's moving to the left with a speed of 1.25 meters per second? So you see, we don't usually want to know the momentum of one thing. We usually want to know the momentum of the total system. So if I were to go and just plug this in, the momentum of the total system would be Sometimes I call these pieces subscript 1, subscript 2, or subscript A and B. So if I call this piece A and I call this piece B, I could say the total momentum of the system, well, it's going to be ma times the velocity A plus mb times velocity B. And this is going to be 1 kilogram times 2.5 meters per second plus 1.5 kilograms times a negative 1.25 meters per second. This is probably where most of the difficulty may come. This is probably where most of the error may occur. This negative sign is telling me that it's going to the left, and many students forget about that, so we can't forget about that. So if I plug these numbers in, this one over here comes out to be 2.5, and the units are not nice, but that's what they are, kilograms meters over second, plus, and this number comes out to be negative 1.875 kilograms meters per second. And when I take out my calculator to add them up, the total momentum of the system is going to be 0.625 kilograms meters per second. So that's the total momentum of the system. I didn't clearly write everything here. I could have said, P total. And then here it would have been, P total. And here it would have been P total. And finally, P total. So the total momentum of this system is 0.625 kilograms meters per second. And if you didn't put in this negative symbol here, you would have gotten a completely different answer, and you probably wouldn't even notice, because you might have said, well, it makes sense what's happening here. The plus sign is implied, and the plus sign would mean to the right. Okay. So we can come back to this problem a little bit later, because what's going to happen is later on we'll be talking about conservation of momentum, and when we talk about conservation of momentum, we talk about what happens right before something happens, right before, like these are going to collide. The way you look at the picture, they look like they're about to collide. So we would talk about right before the collision and right after the collision. For the entire course, whenever we say this thing here, it's a triangle, but we always pronounce it delta. So for the entire course, whenever we've talked about this piece here, delta, this is delta small letter p. We're talking about the change of something. So in this case, we're talking about the change in the momentum. So if there was a soccer ball rolling on the ground towards me, and I kicked it so it's moving away from me, the velocity piece will change. Momentum is mass times velocity. So if the velocity changes, the momentum changes. So when they say delta p, we could expand that. So delta p could equal p final minus p initial. And we could still expand that. We could say delta p equals mv final minus mv initial, because that's what those letters mean. Momentum is mass times velocity. Okay. And then what we could do is we could say delta p equals mass times delta v, which is just the same thing as pretty much what I've been doing. Okay. So what's happening here is that we have a soccer ball, and if we kick the soccer ball and we change the velocity, for example, what's happening here, for example, is we may have a soccer ball, and if we kick the soccer ball, then the soccer ball will change its velocity. And so the soccer ball may speed up, may slow down, may change directions, may stop, but if we're changing the velocity, then we're changing its momentum. And if it's changing its velocity, well, then what has to happen is it has to be changing its if it's changing its velocity, it's accelerating or decelerating. But there should be an acceleration piece involved. And if you remember, one of the things we said earlier in chapter 2, we said the acceleration vector is defined as delta v over delta t. So the way, this was on the side, so the way acceleration was defined is we said acceleration gets defined as we change the velocity with respect to changing the time. So over here, if I do just this one quick thing, if I divide both sides by the letter delta t, okay, let me just change this by the letter delta t. And you may be saying, why can you do that? Well, in math, we can do anything we want as long as we're doing the same thing to both sides. If I follow the order of operations for math, I can divide both sides by delta t, and I haven't changed anything at all. So now what you see is this becomes delta v over delta t, which is considered, this piece right here, it's considered to be the acceleration. So when I see this, I could rewrite it again as delta p over delta t, I haven't changed anything here, equals, this could be written as m, and this could be the acceleration vector. And then I could expand one more time, and I'll go over here, and I could say, well, what does m times the acceleration vector equal? That equals the sum of all the forces. Okay, so they say that you could write Newton's second law. This is Newton's second law. The sum of all the forces equals ma. But they say that it could be written this way also. In fact, that's what, when Newton wrote about his second law of motion in the Principia, his book from 1680 something, he wrote it this way, that the sum of all the forces is equal to the change in the momentum over the change in time. Okay, so that's another way to write Newton's second law. So Newton's second law would be F equals ma, and now we're saying, well, instead of just saying A, momentum changing means that we have some mass that's moving, and the mass is moving in a different way because we're about to change the momentum, which means we have to be changing the velocity of the object. Because usually in these problems we never say, let the mass change. Our mass would be a consistent thing. Our mass could be a soccer ball. Our mass could be a baseball. Our mass could be something that's moving, and you usually are not going to lose pieces of it. So it'll be a constant thing. If we take this and just do one more thing, but I have to erase it. I have to erase some of the stuff around it to show you. If I change this thing, I could also say, if I wanted to get delta p by itself, I could say delta p equals, now they usually just write it this way, capital letter F will say net, and times delta t. Okay, so this is another way to write this piece, and they call this something when you have a force acting on an object for usually a very, very small amount of time. And when I say small amount of time, I'm talking about decimal points. If you had a baseball bat hitting the ball, they'd be in contact for 0.01 seconds possibly. If you had a football being kicked by a foot, again, the contact time is small. Most of the sports work here. If you think of a golf ball getting hit by the club, if you think about the soccer ball getting hit by the foot, the tennis ball getting hit by the racket, even in boxing, if you think about a glove punching another person's face or something, usually the contact time we're talking about is very, very, very small. So this by itself would be called an impulse. So our book uses an impulse is basically this. Some books use a symbol for impulse. Some books use a capital letter I. Our book just calls it the word impulse. So impulse, it is a vector. And I don't know how to draw this for a vector, but impulse is a vector. It has a direction. And what impulse is if somebody were to hit a wall, the impulse would be the force that's being applied to the wall times a certain amount of time, and we call that stuff the impulse. If we rearrange it, and backed it up, if we rearrange it and backed it up, we would call that the impulse force. So you see, when we're if we rearrange this whole thing and backed it up, this piece right here is called an impulse force. So the impulse force, if it's usually a force that happens so quickly that there's a delay reaction before you even notice the force had occurred. For instance, if you hit the baseball bat, if you hit a baseball with a baseball bat, sometimes you'll feel this delayed reaction with a sting in your fingers. It doesn't feel like it happens immediately. And possibly if a teenage child got angry and punched a wall, possibly what would happen is they would feel pain in their hand a slight time after they hit. Meaning, I'm talking about, a fraction of a second. I'm talking probably like 0.12 seconds or something. But it doesn't happen instantly to the person because, you see, there's a time delay for impulses to be sent through our body. So if somebody were to go and hit a wall, they might feel a pain a fraction of a second later. If someone were to be in a car crash and they kind of bang their body around, they might feel the pain a fraction of a second later. So usually these time frames are so small that our brain doesn't even have the signals being sent to the brain yet before that force thing is over. Okay, so as I was saying that this is called the impulse force, and the impulse force usually happens for an incredibly small duration of time. But that will be the time there, and you multiply those two together and you get something called an impulse. Okay. So once again, the idea of impulse, the impulse is a formula: force net times small letter t, delta t. And I forgot to put the units, but the units for an impulse would be newtons times seconds, where it comes out of here. But it also equals, a moment ago I said it also equals delta small letter p. So that means it also equals mv final minus mv initial. So if we put just the first piece and the last piece together, we have something called the impulse momentum theorem. Which equals force net times delta t equals mv final minus mv initial. So with this particular type of formula, they could do many things. They could be saying to you that there is a baseball which is being pitched towards the batter. They could say what the speed is after the batter hits the ball. And they could tell you how much time the bat and the ball are in contact with each other. And then they could ask you how much force was the bat applying to that ball, or how much force did the ball apply to that bat. Okay. These units of newtons times seconds, they're also the exact same thing if you just looked at momentum by itself. Momentum is kilograms times meters over second. It would be the exact same piece. Okay. So let me give you a sample problem with that and see how we do. So my word problem here says a baseball of mass 0.2 kilograms is pitched at 40 meters per second, and it's hit straight back at 40 meters per second. Right back here, I think they meant to say straight back at the pitcher. Okay. So I have to kind of squish that in. So it's hit straight back at the pitcher. Okay, now find the impulse exerted by the bat on the ball. So if you just try to write the formula for impulse, the definition of impulse would be force times delta t. So if you try to do that, you find out that you don't have the force or the delta t, so you can't do it this way. But what you do have is you have mv final minus mv initial. So if I plug these things in, so you just kind of have to think about what's happening. You have to, before you plug it in, you have to kind of picture this situation in your mind. And if I said the original baseball was going this way, and it's going to come towards here, and the batter is going to be hitting it and pushing it away, so the final speed of this ball will be this way, then if I write these in, I would say M, which was 0.2 kilograms, and V final in this picture is a positive 40 meters per second, and then I'll say minus M, which is 0.2 kilograms again, and then V initial was a negative 40, and if I plug those in, what I get is this is a positive 8, and then I'm going to minus a negative 8 with units, and so this the minus a negative 8 comes out to be the negative signs cancel. So I'll have 8 plus 8. So it's going to come out to be a positive 16 kilograms times meters over second. And that would be the impulse. Okay. But usually when they talk about impulse, they want the units to be in units of newtons times seconds. It means the exact same thing. You could spend some time and derive and rearrange those units. But it's the exact same thing as a positive 16 newtons times seconds. And that's the answer. In this case, positive means it's going towards the right. I use the Cartesian coordinate system. Something going to the right on a blackboard would be going along the positive x direction, and we call that going to the right positive. So I'll be saying if this is a positive sign, it's going to the right. So if you think about it, the way I've drawn the picture, I'll show you here. I said the original baseball was being thrown this way. So that must mean someone's standing over on this side, and they're holding a bat. So here I am holding a bat. It's a meter stick. So if somebody was tossing the ball and the ball is coming this way at me, what I would do is I would take the bat and I would try to hit the ball. So I would try to be having the bat push the ball this way. Okay, so which way is my hand moving? My hand is moving towards the right. So I'm trying to push the ball to the right, and the ball will have an acceleration on it, which will accelerate the ball to the right. Which means if the ball is initially going to the left, it's going to slow down very quickly, it's going to become zero very quickly, and then it's going to start to accelerate towards the right and pick up speed as it does that. So that's how to do this particular problem. I have the impulse is right here for this one. Okay, so here is a problem that says we have a test car of 1,000 kilograms, and it's moving at 22 meters per second going to the north, and it is driven into a wall. So this is one of those factory tests they are doing, and the car is going to come to a stop in 0.02 seconds. Two questions. A, find the impulse on the wall by the car, and B, find the impulse force on the car as it's being stopped. So what we have to do is we have to we can draw the situation however we'd like. I would like to go to the right because I usually draw things going to the right. So I will draw the car heading towards this way, and I'll just happen to call going this way would be north. Okay, and there'll be some type of a wall over here. So I'm going to be looking at it in this situation that we have a car driving towards the right, which I just happen to call that direction north, and it's about to hit into a wall. So when it hits into the wall, the car will hit the wall going like this. That is going to be a force of the car on the wall. And what will happen simultaneously? Well, the wall will then be pushing back on the car because of Newton's third law. So this one right here would be the force of the wall on the car. And so those two forces will be equal and opposite, but we are asked to find the impulse first on the wall. Well, I can't. I can't find the impulse on the wall, and that's what they're asking me to do. So the question is, find the impulse on the wall. And I just said I can't, but what I can do is I can find the impulse on the car. So the impulse on the car should equal, well, the impulse is a formula. It's either F times delta T. Now, I don't know what the F is, so I can't actually figure out it this way, but I can say mv final minus mv initial. So if the car was driving along the north, in this case, and it hits the wall and stops, the final velocity is 0. So this is 1,000 kilograms times 0 minus, and the mass here is 1,000 kilograms, and the initial speed of this thing was 22 meters per second. So if I plug this in, I get 0 times anything is 0, and this would be 1,000 times 22, which is a negative 22,000 newtons times seconds. That is the impulse on the car. But they asked, what's the impulse on the wall? So the impulse on the wall will be the equal and opposite idea here. So the impulse on the wall is going to be a positive 22,000 newtons seconds. So there's my answer for A. Okay, so I was not actually able to calculate what is the impulse on the wall, so I used the car because I knew the car was moving and I knew what the two velocities were for the car, so I plugged it all in. Now the second question says, find the impulse force on the car. So the impulse force on the car. So question B says, find the impulse force on the car. So there was a formula that said impulse equals force times delta T. Well, the impulse, and we're looking for on the car, so this is the impulse on car, and this is the force on car. Well, the impulse is this negative number, so the impulse is going to be on the car is a negative 22,000 newtons times seconds, and the force on the car is unknown, and the time they told us was 0.2 seconds. So if we divide both sides by 0.2, the impulse is going to come out to be, the impulse force will come out to be, so dividing both sides by 0.2 seconds, second unit will cancel out, so I will have the force on the car as being a negative 11,000 newtons. So what does that mean? The negative means it's opposite the original direction. And I told you I was going to take this problem and having the positive be north, so that means the negative is going to be south. So we're talking about south here. So we have a car, and the car is coming this way. The car is coming towards me. So to stop the car, someone has to push it in the opposite direction. So if I had something on a cart, and the cart was filled up with an awful lot of books or whatever, science equipment, if the cart was rolling towards me very, very fast and I was fearful it was going to hurt me, I would put my hands out like this and I would try to stop it. I would try to push it out of the way before it hit me. And that might slow down the cart and that might stop the cart. Well, the wall did the same thing. The wall applied an equal and opposite force onto the car. The car pushed on the wall to the right, the wall pushed on the car to the left. And that's why this thing here says the force on the car is going to the left. But the number is, wait a minute, I did my math wrong. I apologize. This number should be 110,000 newtons. So the force on the car would be a negative 110,000 going to the left. There are not many conservation laws in physics, and we've already learned about conservation of energy in chapter 5. So in this chapter we talk about conservation of momentum, which basically means the total momentum of a system, meaning the individual momentum of all the individual pieces added up together. That would be the total momentum of the system. It will remain constant, that number, before and after something happens, and usually we talk about a collision. So before a collision, the total momentum of the system will be the same as the total momentum of the system after the collision. It may be the opposite of a collision. A collision is when two things come together and collide. Possibly you have two things somewhat sticking together and they separate. So if you have two things that are separating, sometimes they show if a cannonball is being fired out of a cannon, or a bullet is being fired out of a gun, or if someone is standing on a rowboat or a canoe and they just decide to jump off. Those are when things are somewhat stuck together and then they separate. So when that happens, we have something also called conservation of momentum. The total momentum before the system will be equal to the total momentum after the system. So it doesn't matter what type of occurrence is going to happen. It could be a collision or a separation. We'll always have conservation of momentum. Here is a word problem. It's very similar to one of the first examples I did when I started this talk on chapter 7. So it says this, that we have a toy cart of 1 kilogram and it's moving to the right at a speed of 2.5 meters per second. And there's a second cart, a 1.5 kilogram cart, moving to the left at 1.25 meters per second. I say if the two carts collide and stick together after colliding, what is the final velocity of that stuck together masses? So they're just forming one thing. So we started to do a problem just like this at the beginning of this talk, like I said, and the number is the same. So what I would usually do is I would draw out the picture, and I would draw out the picture of the beforehand, and then afterwards I would put a little squiggly line down the middle between the two to show you the moment of the impact. So I'm not going to show the impact, I'm going to show the moment before the impact and the moment after the impact, and then I will just say that the total momentum before is equal to the total momentum afterwards. So I've tried to draw it, and what I've tried to do is I've tried to draw to the left the situation that I read about. So I read about a 1 kilogram cart moving to the right at 2.5 meters per second. I read about a 1.5 kilogram cart moving to the left at 1.25 meters per second, and they collide. So what I'm seeing to the left is before the collision. This little squiggly line here, that's the moment of impact. We don't see what happens there. And this right here is going to be after the collision. So I'm talking about 1 kilogram plus 1.5 kilograms. They're stuck together. And this is after. So I'm trying to see what is the final velocity of this stuck together piece. So I would use conservation momentum, meaning the total momentum before the system is equal to the total momentum after the system. So I'll call this piece here A, and I'll call this piece here B. And I'll say the mass of A times the velocity of A initially plus the mass of B, the velocity of B initially, equals the mass that's total times V final. Now I call it total mass because it's just stuck together. There's no difference between A and B right now. They're all moving. They're both moving as one. So I'll plug in the numbers. So I have 1 kilogram here, and I have a positive 2.5 meters per second here, plus I have 1.5 kilograms, and I have a negative 1.25 meters per second. And I'm going to say that equals, the total mass when I add them together is 2.5 kilograms, and V final is unknown. So I've done this earlier today. This was a positive 2.5 kilograms meters per second, and this is a negative 1.875 kilograms meters per second, and that still equals 2.5 kilograms times V final. So when I add these two pieces here together, I will get a positive 0.625 kilograms meters per second, and that equals 2.5 kilograms times V final. And if I take my calculator out and divide both sides by 2.5 kilograms, what comes out is I'm getting a final answer as positive 0.25 meters per second. So the unit of kilograms will cancel out the top and the bottom. And this would be my V final of the whole thing. So that would be how to do this type of a problem. Typically they want a little bit more. When there's collisions, the book talks about certain types of collisions. They talk about an elastic collision. They talk about an inelastic collision. They talk about a completely elastic collision. By the way, this is a completely elastic collision. When two objects stick together, that's the definition of the completely inelastic collision. So they're talking in this particular problem about a completely So what does those words mean, a completely inelastic collision? Well, it's a type of collision when you're going to lose some energy. So if you were to check the energy of this whole system, this piece is moving, so this piece has some kinetic energy. This piece is moving, so it has some kinetic energy. And this piece is moving now. We just figured out its final velocity. So it's moving with some kinetic energy. Whenever they say it's an inelastic collision, we have lost some of our kinetic energy. So some of the kinetic energy that these two had at the beginning, when they collided, some of that moving energy was converted into sound energy because people would hear the collision, or heat energy because you could then maybe it would deform the metal or something like that. So usually the energies that we lose as far as kinetic energy, they usually go into sound or heat. So I could just quickly check and see if I did lose energy in this particular case. Okay, so let me just check for that. The question could be asked, how much energy was lost during this collision? So if I just want to see if energy was lost or conserved, I would go and look at the kinetic energy. So this piece, the kinetic energy there, would be 1/2 the mass of it, 1 kilogram, and the velocity of it would be 2.5, and I'd have to square it, and I'd get a number when I do that on my calculator. The kinetic energy here would be 1/2. The mass of it is 1.5 kilograms, and the speed of it is 1.25 meters per second, and I have to square that. Now it's a negative velocity, but you're going to square it, so it doesn't matter. And the kinetic energy of this combined piece here is going to come out to be 1/2. The total mass is 2.5 kilograms, and the speed of it is 0.25 meters per second, and I have to square that. So if I do those numbers with my calculator, so on the left side here, I just took out my calculator and I number crunched it. So the first piece has some kinetic energy of 3.125 joules. The second piece has kinetic energy of 1.17 joules. And the last piece has kinetic energy of 0.078. So you can see I've definitely lost some. Kinetic energies can never be negative, they can only be positive. So if I add them up on the left, so I ended up losing most of my kinetic energy. I only have remaining 0.078 joules of kinetic energy, but I started with 4.3. So if I divide that, I only have about 1.8% of my kinetic energy remaining. To do that, I took my final amount of kinetic energy and I divided it by my initial amount of kinetic energy, and then I multiplied it by 100 for a percentage, and I got 1.8. So I have about 1.8% of my kinetic energy remaining.